Hi, my name is Scott Simpson, and today we're going to be covering Lewis structures in my chemistry tutorials. If you have any questions or comments, please leave them below. So, Lewis structures are important for chemistry because it gives you a good idea of what the molecular geometry looks like. I'll be covering molecular geometries and electron domain geometries in a future YouTube video. Alright, so first thing is we have to cover basically, why do we even need Lewis structures? So they're important for chemistry because it gives us a pictorial idea of what molecules look like. In reality, these molecules aren't this way, but it's a good way to show this. So first, let's cover how we draw Lewis diagrams. So let's take our first example of H2 gas. So if you notice, this hydrogen has a single electron. You can determine that from the periodic table. If you look and see, if we pair it up with another hydrogen, where I'm going to represent its electron with an X, we get a pair sharing between them. And now, if you know that hydrogen only has the one S available to it, one s orbital, that means there can only be one electron in, or one set of electrons in its orbitals. So, what we have to do then is we draw a bond between them, and that's just represented by a line. So every time you see a line, that's counted as 2 electrons. Alright, let's move up to an example where we have to see an octet. So let's just look at simple water. So we have an oxygen. Now oxygen has 6 valence electrons. We don't care about the inner core shell electrons because normally they're not involved in bonding. But we're not going to talk about that here. Alright, so we know that oxygen has 6 electrons. Now what happens when we have the waters come in? So I'm going to draw a hydrogen here and a hydrogen here. And like last time, I'm going to represent the electrons that the hydrogen owns as X's. So there will be an X here and an X here. So what this translates to is actually a Lewis diagram that looks something along the lines of this. Where again, wherever we have 2 electrons that are forming a covalent bond, we draw a line. If you notice, the lone pairs on these oxygens, they haven't been represented as lines. That's because they're lone pairs. Lone pairs are not shared normally, and so you can leave it like this. Alright. What about when we go to something a little more complicated that's beyond an octet? What if we go to an expanded octet? So let's do something like SO2. So sulfur has 6 electrons. And each of the oxygens at 6 has 12, well, each of them has 6 electrons, so we have to have a total of 12 electrons for oxygens, which means in total for our entire system, we should have 18 electrons. Now, it's always a good idea to sum up what the electron count should be before you go to draw the Lewis diagram, and to double check after the Lewis diagram has been drawn. So, let's see. So we have our sulfur here. The thing I do is I first just draw single bonds to whatever atom we're looking at. And then I say, hey, I know oxygen most likely has a double bond. So I toss in a double bond. How did I know that? Well, oxygen is one of those atoms that oftentimes likes to form double bonds. I'll go through the dot explanation in a second, the one that I had been previously doing. And then we would know our sulfur, if we count our electrons, so we have 2, 4 for our lone pairs on this side, 6, 8 for our lone pairs. So we have a total of 8 right now, electrons, lone pairs. Now how many do we have in the bonds? Remember, each bond is worth 2 electrons. So in this case, we have 2, 4, 6, 8. So we have 8 electrons in bonds. If we sum that up, that adds up to 16 electrons. So we're still missing 2 electrons. So where can they go? Well, atoms that are in the same row as oxygen, they can only accommodate 8 electrons in their valence shell, right? That's what we call the octet rule. But atoms that are lower in atomic number than that row have what they call an expanded octet, where they can accommodate more than 8 electrons. So what we usually do in this case is if we look, right now sulfur only actually has how many? 1, 2, 3, 4. It only has 4 electrons. If we toss 2 on here, then we end up with 18 electrons. So add 2. Now we're at 18 electrons. And that's what we should be at. It matches up with our electron count over here. So we have the correct number of atoms. Now let's say we had something that's charged. Let's talk about that. All right, so let's say we have a simple molecule, hydroxide, so OH minus. How would we go about drawing the Lewis diagram for that? So, we have our oxygen there. We have our hydrogen here. Now, how many electrons do we need? So, oxygen has 6, hydrogen has 1. And that negative charge indicates that there's also 1 additional electron there. So we have to add another electron. So this system in total should have 8 electrons. So what we can do is toss this on like that. And this is okay, except we are not including our formal charge. Now what is formal charge? Formal charge is defined as, so formal charge is equal to the number of electrons of the neutral species minus number of electrons the atom has. So, in our example, we consider, so there are 2 electrons that are in this bond. We consider 1 to be owned by the oxygen and 1 to be owned by the hydrogen. So, oxygen has 7 electrons here, hydrogen has 1 electron here. So let's determine the formal charge for the oxygen. So in neutral oxygen, the valence shell only has 6 electrons, right? So the way that this would work is we'd have 6 electrons, we'd have 6 here for the number of the neutral species minus the number the atom has. So we just counted that. This oxygen has 7 electrons, minus 7. We add that up. We end up with -1. So there should be a -1 charge on this side of the atom. If we do the same thing for hydrogen, let's calculate the formal charge for hydrogen. So should be 1 because hydrogen only has 1 valence electron. And now if we count, it only has ownership of 1 electron. So -1. we end up with a formal charge of 0. So this end doesn't have a formal charge, but this end does. So this end is negative, this end doesn't have a formal charge. Now, we should make sure our formal charge adds up with or is equal to whatever charge was determined up here. So if we look, there's an overall charge of -1, which is great because it matches up with our -1 charge over here. Perfect. Now, let's look at a kind of wacky example. So let's look at this guy here, NH3BF2. So, nitrogen H, B, I'm sorry, this should be a BF3. F, F, F. All right, we're going to have to count all of our, let's change this to an H. This will make this example much easier, actually. H, so get rid of these F's, they're actually H's. All right, so nitrogen has 5 electrons. Each one of these hydrogens has 1, so there's 3 electrons here. Bromine also has 3 electrons. Same with these guys. So, 5. So we're good on our electrons. So it should be a total of 5 plus 9, 14 electrons. So if we count, 2, 4, 6, 8, 10, 12, 14. So we've drawn our Lewis structure correctly, but have we included the correct formal charge? The answer is no. So, why not? So let's calculate the formal charge for nitrogen. So, formal charge of nitrogen. So it's equal to the neutral species minus what the species has. So in this case, nitrogen has, in its neutral state, has 5 electrons. Minus, how many electrons does it have here? Well, we said previously that for each bond we have, you really only count it as 1 electron because the electrons are being shared in a covalent bond. So we have 1, 2, 3, 4. So nitrogen only has 4 in this case. So 4. So 5 minus 4, we should end up with a positive 1. So that means the nitrogen has a positive 1 charge. What about the bromine? Or boron, excuse me. If you can guess already, so boron in its neutral state has 3 electrons, right? In this case, it has 4. So we should have a formal charge of -1 on the boron. Now, does this make sense? We have 2 separate charges here, and do they match up with our original formula? The answer is yes, because if you look at the net charge on this guy, it's 0. +1 minus -1 is 0. So it ends up matching very well with our formula that we have up here that has no charge indicated. All right, so that's how you can go through Lewis structures and draw Lewis structures. We can go a little bit further into this where we talk about electron domain geometries and molecular geometries, but we're going to save that for a different video. So again, if you have any comments or concerns, please leave them below, and thank you very much.